also one screen is not there.
Hmm.
Every time I need to go. Hi, this is Colin from Hearing. I have a problem with the display. I couldn't see in Zoom. EMC 20001. I think this one happening every week. Yeah. So one display is showing the Melbourne campus, the other one is empty. So maybe I need to touch. No, so I think some from. Can you touch that one? Supposed to. I haven't started yet. Okay. Yep. Okay, thanks, bye. Okay, let's see. Okay. So sorry, I think I sent an email last week. I realized that some of the slides are not updated.
Yeah.
So sorry, I did that one. If it is something, just ask me, because the thing is they roll out from the previous year, and sometimes I don't realize that's happened. Okay, so it's automatic rollout from the previous year. Anyway. So give me a second, I quickly open. So let's start. So last week can you hear? Last week we discussed about the design of beam, and we started the T or L shapes at the end of the lectures. So technically at this stage you should be able to know how to do the deflection check. Okay, there are two methods: deemed to confirm method and simplified method. Then how to do the crack control check. There are three conditions. One is enclosed buildings, interior environment. That one, the crack control is generally satisfied with the spacing arrangements. Okay, so they specify maximum and minimum spacing. So with that one, interior beams, or the beams not subjected to the environmental conditions will work. In other cases, we had two methods. We discussed direct method and indirect method. So once you did that one, we also did the flexural strength or the tensile reinforcement design. We haven't discussed shear design, but we will quickly look at the T or L beams because we started this one last week. So when you have slab and beams casted together, we need to consider, because the beam and slab put together, we need to consider some components from the slab comes with the beams. Okay, so when you draw the bending moment diagram, generally the width of the flange, the top part, you can see the width of the flange. This one is generally determined where we have zero bending moment. When you draw the bending moment diagram, so here we have some moment at support, here also we have support moment. So the bending moment diagram comes like that, it goes. So at some places between these 2 points, you will have zero moment. So the width of the flange is determined based on the bending moment diagram. So actually at the end of the flange, the moment will be zero. So that's why they decided. So depend on the location of the beam, it can be L beam or T beam. So when you have L or T beams, okay, the clause 8.82 define what is the effective width. So that means when you consider T beams, so the effective width of the width of the flange, this one, width of the flange, they define in this clause BW plus 0.2A for the T beams, BW plus 0.1A for L beams. So technically T beams means two sides, so that's why 0.2, L beam means only one side, so 0.1A. So the 0.1A is actually zero moment things, that's what I discussed earlier. So it is 0.7 L, capital L, remember L is the center to center distance. Okay, L is the center to center distance. So the 0.7 L is equal to A. So you should be able to calculate the effective width of the L shape or T shape beams. So this is the standard notations. So this is thickness of the flange, this is effective width and effective web. So this is 0.1L and this side 0.1L. So if you had T beams, it is 0.2A. So this is 0.1A, both sides. So if it is a T beams, it's a 0.2A plus BW. If it is L beam, so that's, we have only one side. So that is only 0.1A. So generally we have two cases, flanges under tension or web is under tension. So here this part can be under tension or this part can be under tension, depending on the bending moment diagram. Okay, in the midspan, bottom part will be under tension. At the support, top part will be under tension. You know, the bending moment diagram, if you remember, the support moments are hogging moments, so top part will be under tension. The midspan moments are sagging moment, so the midspan bottom part will be under tension. So we have two cases. Flange is under tension, so flange means top part is under tension. That is normally at the supports. The web is under tension, so that is bottom part is under tension. So the midspan of the support, midspan of the beam. So if it is a flange is under tension, so you can see that tensile reinforcements will be on the top part because flange is under tension, so we provide the reinforcement on the tension side. Yeah, so we provide the steel on the top section, bottom part under compression. So when we work out the equations, if you remember the last week, the rectangular sections, so we always draw something, the top part is under compression, bottom part is under tension. But for the rectangular section doesn't matter because you put upside down, it won't change. Yeah? But here the top part is under tension. So if you just flip the section upside down, okay, I'll show that one here. So here we need to provide reinforcements because this is under tension, this is under compression. Okay. So I don't use to this kind of things. I always have reinforcement in the bottom. So I just flip that section. Okay, so I just upside down. So here this is compression, so we have a neutral axis here, and then we can say that approximate rectangle is, I don't change it, I just for my convenience. Okay, the beam is like that. I can't rotate it in actual case. Okay, I can't rotate it in the actual case, but for the workouts I just flap the section. So this is flange is under tension. Okay. So what will happen when you look at this one? So this is alpha 2 F dash C, and this is gamma dn, because this is dn, this is BW, this is B effective. Okay, so when you work out this one, FST is equal to AST FSY, no change. FC is, it will come up to here. So this much of area. So wherever the gamma, wherever the dn is, it won't go here. So it can change anything, but it is within this web. So alpha 2 F dash C, alpha 2 F dash C, the stress time area, area is depth gamma dn times BW. Okay. So here doesn't matter what dn value is, definitely it is within the web area. So it is very similar as you did in the rectangular section. Only in the rectangular section, if you remember, this is this one, in the rectangular section we use B, isn't it? We use B instead of BW in the rectangular section, because from top to bottom same width, but here it had different width, so we use different symbols, but technically it is same. So if the flange is under tension, that is at support, we don't have any complications in designing this one, because we already did, if you have something like that. So this width of the flange is not a problem, because this part, the concrete, is not exist. Yeah, below the neutral axis, what we said, no concrete. Yeah, below the neutral axis, no concrete. So if you say that something like that, so this part is not effective, the concrete section is not effective. So I don't worry about whether it's a T section or rectangular section or circle. I don't worry, because below that we don't consider any of the concrete. Yeah, so we ignore the concrete below the neutral axis. So this section is very similar to rectangular section, only things V is equal to VW. Okay, but the minimum reinforcement had a little bit different numbers. You need to look at that one carefully. So the minimum steel requirements are slightly different from rectangular beams, but flexural steel calculation, everything is same here as rectangle. If the web is under tension, that is little bit different. Okay, So when the web is under tension, the reinforcements are in the bottom part because in the web's area. So if you look at the section, so here so we have steel here. So the neutral axis can be anywhere, somewhere here, I don't know, okay? So let's say this is a DN, this is TF. So we have reinforcement here. So when you draw the stress block, the question is, this flange is here. So this is TF. Okay. So the question is whether this rectangle, the approximate rectangle, comes below the TF or above the TF. Okay. So it can be above the TF or it can be below the TF. So that means this depth of the rectangular section, this one, okay? So this is gamma dn, this is gamma dn, here gamma dn is less than TF, here gamma dn is greater than TF. Both are possible. We don't know. Both are possible. So if you have such a case, there is a possibility of having the rectangle, so the FC things. So if you have the first case, the area is quite easier. So the area is easier because it's again rectangular section, isn't it? But if you have that this depth comes somewhere here, so you need to consider that section. So in this case, the area gamma dn times width B effective times gamma dn. Yeah. For this case, B effective times gamma dn cannot be used because B effective times gamma dn will give this one. So we need to add this area. We need to add this area and put it here. Okay. So that is a little bit different from the rectangular section. So only when the stress block reach the web area, the area of the concrete will be alpha 2 F dash C, alpha 2 F dash C times the area of this section. Okay. So that is only different. So the T section or L section technically easier except the last case. The stress block reach the web. Okay. In all other cases, it becomes a simple rectangle. So when you calculate the area of the T section for the last case here, we need to calculate this area. The easy way is to consider this section as this one, and the both ends like this. So you can add everything together. So if you work out like this, you can have in different way as well, but this one is easier for the workings. So that's the only different. All other designs are same. Okay. So only when you have the web under tension and the stress block reach the web, then only we need to use this techniques. Okay, so that's a little extension of the LOT sections. So now we know how to deal with the flexural reinforcements. Okay. If you don't understand or anything, just let me know. Okay, because I'm going with this one relatively faster sometimes, because you might know the design of concrete from your bachelor degree, you know? But only thing is we need to look at in the Australian perspective. So we are looking all the things. Some of the things are covered in undergraduate. So if you have any problems, just let me know. So now we know how to do the flexural reinforcement for rectangular section and the T sections. So this one we discussed already. So this is the new part, the shear design. Shear design quite complex, and in 2018 version they have rewritten the whole shear design. Okay, earlier they have different equations for VUC and different methods. Everything has been rewritten in 2018 version. Okay. So what is the shear? So the shear crack generally started near to the support, okay, where you have large shear force. So we need to provide some reinforcement. Sometimes we need, sometimes we don't need. So how to know whether we need the shear reinforcement or not? To get that one, we need to know what is actually happening. Okay, there are 3 videos that shows the failure of so So we have some videos, please have a look. This one, some useful videos. Okay, so how to design like a longitudinal reinforcement? We need to know the process. Okay, so when you have the shear cracks, that means a reasonably large shear force and the bending moment, we will have a combined effect. You might know the Mohs circle. So based on that one, the maximum principal stresses will be able to calculate. So if you can calculate the maximum principal stress, so when the maximum principal stress equal to shear capacity, you should be able to decide whether you need the shear reinforcement or not. So that means the shear capacity, we have two things. Shear capacity of the beam comes from two components. Concrete itself can carry some shear force or shear stress. So the shear capacity of the beam is given by clause 8.2 equation. The shear capacity of the beam Vu is equal to VUC plus VUS. Okay, so two components, VU is equal to VUS and VUC. So the condition is same, V star should be less than or equal to pi time VU. So now we will see the pi value is 0.75 and we will see how to find out each and every component, VUC and VUS. VUC is the component, VUC is the component from concrete. So how much concrete alone can take. So if the concrete component is sufficient, sometimes the VUC is quite large, especially in the slabs. VUC itself can satisfy the V star is equal to less than or equal to pi VU inequality, so condition. So that means in slab generally VUS equal to 0 normal. So that means we don't need any shear reinforcement in slabs. That is a general case. We can check it, but that is a normal case in the slabs. So to calculate this one, VUC, the contribution from concrete, is given by this equation, KV dV BV times square root of FC. So what is that each terms means? We'll come to the KV in a minute. The dV and BVs are new terms. The BV is the width of the effective width of the beam. Okay, so if you have beams the width of the beam, so it's either B or BW. Okay, B or BW. That is the BV component. So we have two new terms, KV and DV. BV is the width of the beam, and FTC, you know, strength of the concrete. So that is known. So if you look at the KV, KV is given as these equations in clause 8243, clause number 8243 explain how to find out KV value. So that clause is called simplified method to calculate KV and theta. Theta, we don't use it yet, but it will come in the next slide or two. So they define KV and theta V, but at the moment we don't need the theta V. Theta V only need for the shear reinforcement capacity VUS. We will come to that one in a minute. So KV is given by this equation. It can be either 0.15 or 200 upon 100,000 plus 1.3 dV. So when you do the design, the first one is we need to calculate the V star. That normally comes from shear force diagram. So you can use a space case or section 6.10 to find out the V star, that is a maximum shear force. Then we need to check the dimensions of the beam is adequate. The standard says VU max, which is the maximum shear force the beam can carry. VU max is the absolute maximum. It cannot go more than that. So the VUS need to be checked, because otherwise you can't satisfy shear design. And then they said if it is less than VU max, that should be okay, otherwise you need to change the section. Okay. So if the V star is less than VU max or pi VU max, then your section is adequate to carry the particular shear force, whether without shear reinforcement or with shear reinforcement, but your section is okay. Okay, so VU max is generally very large value. So then we will calculate the pi VUC, that means component from concrete, and check whether the pi VUC itself can carry the shear force. So we'll calculate VUC, and if that one is the case, if the V star is less than pi VUC, we don't need any shear reinforcement. So that means if it is less than pi VUC, we don't need any shear reinforcement, so that's it, finished. Otherwise, we need to do the shear reinforcement design. So that means you need to calculate VUS, and from that you need to calculate ASV upon S, and we need to provide the shear reinforcement. So that's the steps as we normally do. We will work out the question work out the question, tutorial question in the tutorial time. So this is about slab design. The slab design, if you know the beam design, slab design is quite easier. Especially the slab supported by beams, whether both sides or all four sides. If the slab is supported by beams, the design of slab is much easier than beams. So the bending, flexural reinforcement design is same as beam design. Okay, there is no different. And we don't need any shear reinforcement. Usually slab don't need any shear reinforcement. We will also check for deflection. So in slab design, normally the deflection is the more complicated or problem parameter. So if the deflection check pass, your design is almost okay, done, because its flexural is quite straightforward. So we have different type of floor or slabs. The first one is a flat slab. You can see there is no beams. Okay, the first one is a flat slab. You don't have any beams, so we will look at this one in the next week, because they scheduled for this week, but if you put everything together it will be confused. Okay, so I will, once we did the tutorials, we will look at the flat slab. So the second one is a band beam. So you can see the width of the beam is quite large compared to the depth. So that is called band beam. So normally the band beams are used in one-way slabs generally. So that means you can see the beams are on the both sides here and there. So the load from slab will go half this side and half that side. Okay, so only in one direction the loads are transferred. So that is called one-way slab. And for one-way slab normally we use band beams. So that means the depth of the beam is quite small compared to the depth of the beam. Okay, the depth of the beam is very small compared to the width of the beam. So that is a band beam slab arrangement. The next one is a composite slab. So sometimes, you know, the formworks are made of timber. Sometimes they put some steel like this. Rather than putting reinforced bars, they put steel plates or sheets underneath. So this one, you can see this part will work as a steel reinforcement. Okay, and the bottom part will work as a formwork. We don't remove that formwork, so it will stay there. So it's easier for some construction works. But again, the area of the plate or sheet, cross-section area or thickness of the sheet is limited. So for the larger span, sometimes it's become problem, but otherwise normally should be fine. So this is the two-way slab. You can see the slabs are supported by beam in both sides, also all four sides. So the load will go in that beams as well as that beams. So that's two-way load transmission. So that means two-way slab. So generally the slabs are classified into twos, the flat slab and the slab supported by beams. That's what we are going to study this class. And tomorrow, or next week, we'll talk about the suspended slab or flat slab. Okay. And if you look at the slab supported by beams, we can classify into two different cases: one-way slabs and two-way slabs. One-way slab is slab supported by only both sides of the slab. Two-way slab is the beam is supported by all four sides or three sides at least. So again, I explained this one. One-way slab is loads are transferred in one direction. Two-way slabs are loads for transfer in both directions. Okay. So, and they have a standard notation. If it is a one-way slab, it's basically Ln, only one direction. If it is two-way slab, they have a notation Ly and Lx. Lx and Lys are not x-axis, y-axis. Okay, it is not the case. Ly is always larger than Lx. So when you have a slab supported by beams in four sides or three sides at least, we define some spans in both direction. So for our convenience, shortest span is defined as Lx, largest span defined as Ly. Okay, so it is not xy axis, it is shorter and longer. And this is the definition. I think we discussed this one earlier as well. L is the center to center, clear span, effective span. The fractional span, LO, sometimes it also comes. LO is equal to N minus 0.7 times L support left, L support right. Okay, so 0.7 times that supporting beams. So these are given in the standard notation. So there is no proof or anything. Basically you take as it is because they define. So in the slabs we need to check for bending. If it is two-way slab, both direction. Flexural shear, normally that will be satisfied with VUC. We don't need any shear design. The punching shear, normally around the columns or any large point loads. Something like a steel cabinet sitting on the floor of the slab. So very large load over a small area. Okay. So that is called punching shear. So this comes under shear ultimate limit state. The other one is a serviceability limit state, deflection and cracks. So we need to make sure our design satisfies both ultimate and serviceability. But normally we don't do the fractional shear design in slabs, but as you are doing first time, it's better to do it the calculation. But in the assignment, if you want, you can say that normally we don't need to provide any shear reinforcement. So we need to consider 1 meter strip. I will explain that one in a minute. Then do the deflection check to ensure our effective depth and the overall depth of the slab is satisfied for the deflection as well as durability and fire resistance. Then we need to determine the AST, tensile reinforcement, using bending moment, minimum reinforcement and crack control. Okay, so generally we will provide more steel than use that. Fractional shear we don't need actually. Punching shear we need to check it under according to clause number 9.3. Okay. Torsional reinforcement only if necessary. That means if you have any torque due to some components other than the beams and slabs. Then we need to look at the deflection check. So the deflection check can be done either simplified method or deemed to conform method. You can do one of that. So once you did all the design, this is the detailing. So before we go into that one, I will show. So the one-way slab, you have a beam here. So here these are the beams, okay? Beam 1, beam 2, beam 3, beam 4. We don't have any other beams, so it's continuing. So the loads will transfer from this slab to this beam and this beam. Half the load will go. Okay. So when you design this beam, this will deflect like this. Okay. So it will deflect. This is the span, not this one. Okay. So when you look at that one, we need to design the slab this way because the deflection will happen. So we will take 1 meter strip, 1 meter strip, so if you look at this one from here, if you look at this one from this view, so you have a 1 meter strip beam and we have B1 here, B2 here, B3 here, B4. Okay. So we need to design this one. So this is one-way slab. We can use clause 6.10 to draw the bending moment diagram. Okay, because it's a continuous beam kind of things, 1 meter strip, so like a 1 meter width beam. Okay, this is like a 1 meter width beam, so we should be able to calculate the load for the 1 meter strip. So it become like a beam with 1 meter width, so we should be able to do the same things whatever we did in the rectangular beam. So we need, that's what I said, the rectangular beams are very important. So if you know the rectangular beam, the one-way slab is quite straightforward. Okay, it is a 1 meter strip we take, and that become 1 meter width beam supported by these beams. Yeah, so that is quite easy. But if it is two-way slab, we need to consider the strip in both direction. Okay, both direction. So we need to do 2 types. One is B to B and A to A. So if it is a two-way slab, that means supported by 4 sides, you need to design the slab in both directions. It's the same repeated work, but you need to do in both directions. Okay, so you calculate the bending moment diagram using clause 6.10, but there is a different table for two-way slabs. Once you have that one, you should be able to design the flexural reinforcement for AA direction and BB direction. 2 separate design. 2 separate design. Repeated calculation with some numbers different. So once you did everything, we need to do some extra reinforcement for torsional effect, especially in the corner reinforcement, where you don't have any continuation, of the slab. So in the corner panels, need some extra reinforcements. So they explain in 9133. So it comes under the detailings. I will explain that one once we did all the design in the drop-in session. So as a quick summary, one-way slab, reinforcement predominantly in one direction. We need to check the minimum reinforcement still. We need to do the shear check design requirement, but everyone knows the shear reinforcements are not required. But please check that one in the assignment. Okay. For two-way slabs, you need to do for both directions. Okay, you need to do the same thing as we did in the one-way slab, but in both directions. For corners, we need extra reinforcements due to torsional effect. So they said you need to put some additional reinforcement as a mesh format. So we'll talk about that one in the detail. Okay. So in the two-way slabs, you need to be a little bit careful because we need to provide the reinforcement in both directions. Okay. So when you look at that one, we have both directions. As you see, the bending can happen in X direction and Y directions. X is the shortest span, Y is the longest span, not XY coordinates. Okay. So we have bending moment in X direction and Y direction, which is shortest span and the longest span. In clause 6.10, there is a table and equation to get the bending moment in X and Y direction for two-way slabs. Okay, I will show that one. I will show that one during the tutorials. So if you have bending moment, you should be able to find out reinforcements. So when you calculate the reinforcement, we need the effective depth. So you know the reinforcement need to be provided in both direction in X and Y. So when you provide the reinforcement in two directions, one layer should be on the bottom, other layer should be on top. You know, it's crossing, it will cross each other. So you need to say if it is a two-way slab, so okay, it is one way, but if it is a two-way slab, you may need to provide reinforcement this way as well as this way, okay, for both directions. So one of the layer should be bottom, and so something like that, and another layer should be on top of that. Both can't be in the same level, yeah. So one will be below, another one will be on the top. So which one should be on the bottom and which one should be on the top? So generally the shorter span will go below because that have larger bending. Shorter span will get the larger bending. So we need the larger effective depth. Shorter span will get larger bending. So we also need the larger effective depth so that it become more optimum design. So shorter span will go on the bottom. So that's why you can see the shorter span you'll have reinforcement this way, longer span reinforcements. So the dx is large, okay. The shorter span direction reinforcements goes, so that will go on the bottom side of the layers. So dx is larger. So even though that both directions calculation is almost identical, the effective depth is slightly different, okay. Almost same calculation, bending moment is different and effective depth also different. Otherwise it is almost repeated calculation. So yield line theory, generally the two-way slabs fail something due to loads, and the failure analysis, for the failure analysis we use the yield line theory. So yield line is basically the weakest line, weakest energy lines through that the failure will occur. So generally the red lines are the weakest energy lines. So in two-way slab the cracks will happen in that zones, okay. So when you have this loads transfer, as we discussed, I think earlier as well, I put a separate video for the load estimation. It have rectangle, sorry, it will have a triangle distribution on one side and trapezoidal distribution on the other side. Okay, but we know, I think we discussed this one in the beam design, we need the equivalent load. Okay, the equivalent loads are given in these slides. So that means rather than considering triangle distribution and trapezoidal distribution, we need to consider a uniform distribution or uniform load distribution. So the equivalent load distribution, equivalent uniform load distribution is given by this equation. So you can use this one and get, I think we used, or we discussed this one in the last week. Okay, but for the slab design we don't need to change the equivalent load. For the beam design we need. Okay, so that's basically the slab design. As I told, that the design is very similar to the rectangular beam. The design is very similar to rectangular beam. So make sure you understand the rectangular beam design. If you understand that one, slab design is quite easier. Okay, even it's less work. Any questions? Any questions? We have one more section before we go into the column design. This is week 4. This week is one and the flat slab, but what we do is we will move that one to next week, because we need to do, we haven't done lots of tutorials in shear and the slabs. So once we finish, we will do that one, because week 6 is the advanced topic. We should be able to take a little bit time from there, because we don't have any tutorials in week 6 for that advanced topic. Okay, so we will finish everything by week 6, but slight movement in the schedule, because otherwise you will feel lots of things we don't understand anything at the end. Okay, so I think most of you did this slab design supported by beams in your undergraduate, but the flat slab is maybe a little bit new. Have you done the flat slab design? The
No,
slab
sir.
supported by columns, no beams. Yeah, normally we don't cover, sometimes we cover. In undergraduate here we touch that one, we don't go into the detail, but we will look at the details of the flat slab. I think the level 1 you need to design as a flat slab in your task. Okay, any questions so far? If you want, I can start the flat slab, but it may be a little bit confused. It's both are slab, it's a little bit different approach. Any questions? No? So there are tutorials. We will discuss about tutorials tomorrow. Is there any other